My name is Deshane, and I'm a senior machine learning engineer slash data engineer at QDAS. And a little bit of background about myself. I did software development for many years, but the last 7 or 8 years, I've been focused on data science and machine learning. And I can tell you it's been a very exciting journey. Next slide, please. So today's agenda is to discuss sort of the basic steps of machine learning using Python in the Databricks environment. So we'll do an overview of machine learning, then an overview of data preprocessing, which is a very important part of machine learning, then overview of the model training and validation, and discuss the results of implementation of a sample healthcare related data set. So that is the agenda for today. And I know there are various levels of expertise in the audience. So this is kind of targeted towards somebody who's maybe interested in moving from doing ML from R to Python, or maybe somebody who is getting into machine learning using Python. So it's kind of an introductory level approach. Next slide, please. So let's start out with, what is machine learning? It's a subfield of computer science where, computers learn from data without being explicitly programmed. So in the next slide, there's a graphic which kind of explains that in more detail. So next slide, please. So we have a diagram here at the top. It depicts the traditional computing model.
Machine learning. ML is an umbrella term for solving problems for which development of algorithms by human programmers would be cost prohibitive, and instead the problems are solved by helping machines discover their own algorithms, without needing to be explicitly told what to do by any human-developed algorithms. This is from Wikipedia.
Sorry about that. I think my Siri took over for a minute there. So at the top, you find a graphic which describes the traditional computing model, and where you have an input to the computer, and then you have an algorithm which you write in your favorite language, and then outcomes and output. So that is the traditional computing model. But in the machine learning model, we have an input and output, going into the computer. And through what we call a training process, the output of that is an algorithm or a model. So the data is the key in the machine learning model, and the output would be a model that we can use to predict what, something based on new data. So next slide, please. So just to give a timeline on machine learning in a historical perspective, AI and machine learning has been around since the 50s and 60s and 70s. And it really started flourishing in the 80s and 90s and the 2000s. But it really took off in the last 2 decades, especially with the advent of so-called deep learning, which is another name for neural network-based machine learning. And one reason for this is the confluence of 2 factors. That is the availability of very high-powered compute and lots of data. And those are the 2 things that are needed to develop all these exciting advances that you see recently, things like self-driving cars or language translation, or the latest and greatest that everybody's talking about, the LLMs, that's like ChatGPT, etc. So a lot of exciting things happening in machine learning right now. Next slide, please. So let's talk about the types of machine learning. The 2 major types are supervised machine learning and also this unsupervised machine learning. So what we mean by supervised machine learning is that, let's say the idea of machine learning is that you have a set of features or variables and that produce some outcome, let's say the price of a house. And it can vary based on, the square footage, the location, the city where you're in, all those are the features. And the outcome that we may want to predict is the price of the house. So if we have a lot of historical data with that kind of information, with the features and the outcome, they're also called labels or the target variables. Then if we have that data available, then we can build a supervised model. And some of the examples of supervised machine learning are linear regression, logistic regression, decision trees, support vector machines, random forest, and of course, I didn't add deep neural networks. I mean, those are the major machine learning models that are really built today. And so those are some of the examples of supervised machine learning. Next slide, please. Some of the types of unsupervised machine learning are clustering. K-means clustering is one of them. Let's say if YouTube want to segment the people who come to the site based on various characteristics, based on their demographic, their interests, their age, etc. So they don't have explicitly labeled data on that, but using some of the features, the characteristics of the user interactions they have with the videos, etc., they can segment them into different clusters by using an algorithm like K-means. So you don't need labels for those. Another kind of unsupervised machine learning is principal component analysis. It is primarily used for reducing the dimensionality of a machine learning problem. Some of the problem may have hundreds of thousands of features. And if you have that many features, it becomes hard to train model, very expensive computationally. And so the one PCA is one method that's very popular in reducing that dimensionality. And there's something called autoencoders. So that's type of deep neural networks that are commonly used for anomaly detection. So it has a specific architecture. It can also be used for reducing dimensionality of a problem. Next slide, please. So now let's talk about data preprocessing. I think there's one slide before this, the previous one, please. Yeah, there you go.
Sorry about that.
No problem. So data preprocessing is the most important step in machine learning. So data scientists and machine learning engineers spend about 60-70% of the time preprocessing the data. The data quality and the data in the right format is very important to train an accurate model. So let's look at some of the steps that are involved in data preprocessing. Things like, in real world, data is not clean, right? We all know that. There are missing values, there are outliers, which really doesn't add value to the overall problem. Maybe there are because of mistakes in measurements or errors. So those needs to be eliminated. For missing values, there are various techniques like imputation, and there are various types of imputation. And if there are numbers of those missing values are small, maybe you can remove them from the data set. So those are all ways to handle those kind of issues. And then there is data transformation, called one of them, which is normalization, which means like is scaling the data from something, let's say, 0 to 1. And what that does is, let's say, for some features vary from 1 to 10, the other varies from in the thousands. So that can have some variables with high ranges can have an outsized impact on certain models. So it is beneficial to scale them to like a common scale. Still, maintaining all that variability in the distribution. So normalization is one way of doing that. And standardization is another rescaling, in which you scale the data so the mean is 0 and the standard deviation is 1. So all these methods, can contribute to developing a better model. Next slide, please. So then another important data preprocessing step is dealing with categorical data. By categorical data, what we mean is that the only thing that a machine learning model can understand is numbers. But in the data set we have, a lot of the data sets have columns which are string types, like text data, like the gender of the population, or where they work, or male or female. Those kind of different textual data needs to be converted into numbers. And there are different ways of handling that. One hot encoding is one way of doing that. And label encoding is another type of assigning unique integers to each category. So that's an important step that we have to do. And the next one is sometimes you might have to create new features. So And why would we want to do that? Again, our ultimate goal is to produce a model that will generalize to the data that it has not seen, and also try to pick up the underlying features of the data set. So things like binning, which means that you put like a continuous variable and then put that in different buckets, and something called polynomial features, in which you take a feature called X and then you actually square that, or maybe cube that, in order to capture some of the nonlinear effects of some of those variables. Then there are something called interaction variables you can create. There's a feature called X and Y. You multiply X and Y, then create a new feature. And that can maybe model some of the interaction between two of the features. So those are some of the different features regarding the processing step for creating new features. Then there's dimensionality reduction, like we talked about, applying PCA and something called TSNE. So those are all good for visualizing and also improving model performance. Then for things like image data and text data augmentations can be an important step, because sometimes there's only limited images that you have available for, let's say, doing an image classification task. So how do we increase that data set? The more data that we have, the more generalizable model that we can build. So we can generate more artificial data by, let's say, rotating the images or cropping the data. And for text data, you can create, we can substitute words with their synonyms. So that's how we can create extra data to build a better model. So in short, data preprocessing is a very important step in ensuring that we have, we can build a good model. Next slide, please. So next we talk about model training. The first step in that is that we divide the data set into training, validation, and testing. So we set up you set up 70 or 80% of the data for training and maybe 5% for validation, which is actually used for in the training phase of the machine learning process. And then after the training is done, you use the model that we built on the test data that it is not seen, and that's how we evaluate the model. So like I said, the common split ratios are 80%, 80-20, could be 70-30%, depending on the data set. So, so that's the first step in model training. Next slide, please. So evaluation metrics. So what do we mean by that? So once we build the model, we need to evaluate the models. So we can use various metrics for that, depending on what kind of problem that we are solving. If it's a classification problem, then we can use something like accuracy, precision, and recall, or F1 score, which is kind of a combination of precision and recall. Or if it is a regression problem, we're trying to predict a continuous value. You see something called MSC, is mean squared error, or RMSC, which is the root of MSC. So those are popular, evaluation metrics. So we will use the model that we build on the test data and evaluate using these metrics, and we decide whether this model is satisfactory for release into production, or go to the next step. And if you are not happy with your model, what do we do? So there are two things we can do. So we can go back and one of the first things we want to try is what we call hyperparameter tuning. What we mean by that is that every model, whether it's a classical model like logistic regression or random forest or deep neural network-based models, there are a lot of parameters that you can tweak and tune to try to improve the performance. For example, if it is a neural network model, there's you build this layers of multiple layers. You have an input layer, there are hidden layers, then your output layer, and then each of these layers, the number of neurons. So these are all decisions that we can make and change in order to try to build a better model. So that's what is called hyperparameter tuning. And there are different methods and libraries out there which will help you with just that. Things like grid search is very popular, random search, and Bayesian optimization. These are all some of the popular hyperparameter tuning methods that are used in the industry. Next, I think we are almost done with the slides, I think. Is that right? Yeah. So now I'll move on to the slide, to the notebook, the Databricks notebook, where we implement one of the data sets that we mentioned. So I'm going to share my screen. Julia, am I able to do that now, or?
Yep, you can go ahead.
Okay, all right. All right. Are you able to see my screen?
Yep, we can see it now. Thank you.
All right, thank you. So what you're looking at is a Databricks, it's a Jupyter notebook hosted on our Databricks environment. And it's attached right now to a QDAS compute cluster. So I know Derek went over a lot of the details of Python programming, on Databricks. So I'm going to just focus on the ML aspects, right? So we start off with importing the necessary packages. Like he mentioned also, NumPy and Pandas are very important for machine learning, pre-processing, data analysis, etc. So that's what we're doing here. And in the next cell, importing a bunch of libraries from sklearn. And this one library that you cannot do without is sklearn. It's called scikit-learn. It's a Python library for machine learning. So it has all kinds of classes and methods for model building, pre-processing, evaluation metrics, post-processing, anything you can think of related to machine learning that you can find in scikit-learn. So if anybody wants to do Python machine learning, this is a library to get hold of and understand, and start with. Then we also import Matplotlib and Seaborn for visualization purposes. So that's also an important part of the data analysis. So the data set that I'm going to be working with is one from Kaggle. It's a stroke prediction data set. As you all know, Kaggle has lots of data set that people post and then and post studies about that, analysis about those, which is a great place to learn data science and machine learning. In the next cell, so what I'm doing is using Spark to read. So first I uploaded that data to an S3 bucket location, and I'm loading that into a Spark data frame first, because a Spark data frame supports that kind of a functionality. Then since for data analysis and data pre-processing, the Pandas data frame is a better choice for me. And I'm dealing with, it's a small data set. So I don't need, the distributed capabilities of the Spark data frame yet. So I'm converting that into a regular Pandas data frame here. So, and I just print the columns of that data frame. And as you can see, some of the columns are ID, gender, age, hypertension, heart disease, whether they've been married or not, work type, residence type, glucose levels, BMI, smoking status, and stroke. And stroke, that is our target variable. So that's what we are trying to predict. So all the others are the input features. So in the next cell, we use this head method from a Pandas data frame, which lists, the top, let's say, X number of records. The default is 5. You can specify whatever number you like as an argument. So just to take a look at the data, what it looks like. This is part of that data exploration that we do. So if you look at that, the gender is, of course, a categorical variable. Hypertension, 0 means, they don't have hypertension. 1 means they do. The same with heart disease. And if you look at BMI, so you have, so that's a numerical, value, right? But some of them have NA value because that value is not available for that particular person. So that's a problem, right? So we can't have the machine learning models only can accept numbers. We need to convert that somehow to a number, right? So Pandas has a handy method called toNumeric. So we take that column, BMI column, and convert that into a numeric column. So what happens is that it create when you convert like a string to a numeric. I mean, it doesn't know what value to put, right? So it puts null value, so the NaN in the Python type. So that's what it does in that cell there. And then in the next cell, I run this method called isNA, which is a Pandas method for counting the number of null records in a data frame, and for each of these various columns. So if you look at BMI, it has 201 null records, which is a result of the conversion that we did earlier. So, of course, we cannot have null values. We have to do something with that. So the one thing we can do is imputation, as we talked about earlier. So the fill-NA method of the Pandas data frame can be used to impute null values. So in this case, I've used the mode, the most frequent value of the BMI across the data set as the imputation value here. So once I do that isNA method again and see how many null record, how many records have nulls. So as you can see that BMI doesn't have any more null records. So we have taken care of that problem. Then to illustrate some of the useful methods that Pandas has, value counts. So it'll list the frequency of some of these values, how many people have, value of 28.4, So these kind of analysis can be useful to get an idea about the data distribution, etc. In the next cell, I use the describe method to kind of get a basic statistics of the data. Things like, I know Derek talked about it also, the count, mean, and standard deviation, and min and max, etc. In the next cell, so the ID column doesn't add any value, just a database primary key, right? So that doesn't add any value to our study. So we use the drop method to drop, that column. And you will notice this flag called in place is equal to true. It will be very common in a lot of the data frame methods. If you use that, you can, you don't have to replace this variable. Otherwise, you'll have to return this to another data frame variable to get that change affected. So if you use in place, it makes that change in this data frame variable itself. So that's one thing too. It's good to know that. So in the next step, we're kind of dividing the features into categorical features using, the D types method, and numerical features, sort of for convenience and kind of visualization purposes, as you will see in the next few cells. So, and from the numerical features, we remove the stroke. As I mentioned, this is our target variable. So we want to remove that from the features, right? So that's what we're doing there. And if you print out the numerical features, age, hypertension, heart disease, the glucose level, and BMI, those are the numerical features. And the categorical features are the gender, married, work type, residence type, and smoking status. So in the next cell, you can use the unique function of the data frame, the Pandas data frame, to list what are the unique values in each column. So, it prints, the unique, female, male, and other. And then we have, yes and no for the ever married and self-employed, private, different categories like that. So you can detect all the unique values in a particular column using the unique method. And next come kind of an important plot that tells us something about the data set. So we are plotting the target variable, the stroke. What is the distribution of that variable in the data set? So as we can see that 95% did not have stroke in this data set, 5% had. So this is what is called a highly imbalanced data sets. And highly imbalanced data sets are a problem that we have to deal with in machine learning. It has to be addressed some way or the other. So there are different techniques for that. So what is the reason why we had to handle that? If we don't handle it, then if you develop a model with a highly imbalanced data set, then the model doesn't have an opportunity to learn the features of the minority data set. So that when we are done with the modeling and we pass it some new data set, so it doesn't have enough, knowledge. It doesn't capture all the features for this minority data set. So the model may not be very accurate. So there are a couple of different ways of handling that problem. One is oversampling, the minority data set. There's a method called SMOTE. It creates synthetic data based on the minority sample with the similar distribution characteristics, which is what we'll be using later on in this analysis. And you can undersample the majority set. That's another approach. So, but this has to be addressed in our data preprocessing step. In the next cell, we're building like a method to do some visualizations, just to get a feel for how these variables stack up against each other. So as you can see that in the gender distribution, there are more female than male in this population. They're more married than not. And then more people work in the private sector. Not sure if that had any impact on stroke prediction. Urban versus rural, almost even. Never smoked is higher than other categories. So you get a feel for the distribution. The same thing we do with numerical features. We are plotting the age, in the form of histograms. The ages ranging from 0 to 80 or 90, and it gives a count of how many people belong to those buckets. And here we plot, how many people have hypertension versus not. The same with heart disease and glucose level and BMI. Here we do some bivariate analysis. How do these features stack up against the target variables? Like how many male versus female had a stroke, that kind of analysis. So this kind of visual analysis is very important as part of any kind of pre-processing. So now we are almost getting ready to do the training part of the analysis. So first thing we do is from the data frame, we drop that stroke column. So that will give us all the input features, which we call X. And if we just take only the stroke column, we are just isolating that. And that is our Y, which is our label, because this is a supervised machine learning problem. So we got our X input features and our target labels. Then we use this scale-learn method called test, train, split to split the data, like we mentioned, to whatever proportion that you choose. In this case, you chosen like a 70-30% proportion for test versus training. So we get our X train, Y train, which is what we're going to use for training, and X test and Y test for the testing part of it. In the next slide, we are installing a library, the SMOTE oversampling library that I was mentioning earlier, and we can use either ampersand or the pound sign. But if you use ampersand, that kind of restart the Python interpreter. So so that's why I didn't use that in this case. So we're just installing that packet in that cell. In the next cell, we're importing some more libraries, helper classes that can be used, that can make the model building process a little bit more clean and intuitive. Things like pipeline classes can be used to reduce some of the boilerplate code that happens, in a lot of the machine learning code. So basically, you can assemble a collection of steps and apply them sequentially and execute them one at a time. So that's what that pipeline class does. And column transformer, we'll see later on what that does. A simple imputer is, again, one imputing class we could use. SMOTE is the oversampling method that we're using to address the imbalanced data set. So using this pipeline, we could create two pipelines. One is a numerical pipeline, so for which use a simple imputer with a strategy of median. And in this case, as we looked earlier, we kind of resolved all the null issues, really, right? So this is just for illustration purposes. but you could use the simple imputer with the different strategies, median or mode, or those kind of different approaches. Then for scaling the data, using a standard scaler, another sklearn library. And for categorical variables, we're using the simple imputer with the most frequent approach, and we're using the one hot encoder for the labeling or encoding the categorical features. So that's going to be implemented because we have several, categorical features. So we're going to be using that one hot encoding for encoding those variables into numerical data. And then we create column transformer. So it's another helper class for separating the numerical and categorical features and applying them separately. And we create this mode class, instantiate that in order to include that as part of our pipeline. The next step is we choose the model that we're going to use. We're going to use the logistic regression because this is a classification problem. It's like a binary classification problem, right? We're trying to predict when somebody else might have stroke or not. The logistic regression is a widely used model for that. So we instantiate that class. And then we put all this together in the pipeline class. So we start with the preprocessor, then we apply the oversampling, then we apply the model. So once we put the pipeline together, then we call the fit method and pass the X train and the Y train, our training data set. And this does the training process. And in this case, it's a very small data set. It doesn't take much time at all. But this is sometimes, if you're talking about, huge models, for example, GPT-4, I read that it took weeks and months to train that model. It had like 175 billion parameters. So it took that weeks and months. Some models can take that long to train using all kinds of distributed computing infrastructure. But ours is a very tiny model, so it took only a few seconds. So once we do the training, we have the model that we can test. So then the next step, use the predict method of the pipeline and passing the X test, the 20% or 30% that we set aside for testing, and pass that to the predict method. So that is our predictions. So these are predictions, as to, which of these people will have stroke or not. So this is the data that the model has not seen yet. And the next step is something called the score. It's another method from sklearn. So AUC score is kind of an evaluation metric, which is called area under the curve, which is used in classification problems, which kind of gives both weightage for precision and recall, and it's considered a good metric for evaluating classification problems. And it prints out a value of 0.76. So that's considered a good model. So anything like a random model is 0.5, so like a coin flip. But the closer the values to 1, the better the model is. So this kind of says that's there's 76% chance that this model will predict the correct class for that particular person. So, but this is a pretty clean data set, small data set. So even with the minor pre-processing, we're able to get a pretty good model. And another popular evaluation metrics called confusion matrix, in which we can print the true positives, true negatives, false positives, false negatives, and in a nice graphic. So we use the confusion matrix display method or class from the sklearn. So that's what we are doing here. So essentially, we have trained, gone through the entire process. Then I just wanted to also try a different model, so we used logistic regression. Then we created something called support vector classifier, SVC. That's another classifier. So I instantiated that class and created another pipeline, second pipeline. The only thing that changes is the model, and went through the same steps, fit the model or train the model using the training data. And then once the model is trained, do the predict, get the prediction values, feed that into the test actual versus the predicted value, and get the AUC curve. So we got 0.766, so slightly better than the previous model. So in a normal ML process, we will try different models and see, which one does better. And sometimes we may use a mix of model or average of models, which is called the ensembling method. So that's sometimes used. So like I said, the modeling process is not strictly, like you do one thing and then you're done. You have to experiment. Sometimes you have to go back to hyperparameter tuning. Sometimes you may have to go back to your preprocessing. It takes a lot of iterative steps in order to achieve a model that is satisfactory. So that kind of concludes my presentation.